Hey there, Stanley Lake Physics. We are here today to do a house wiring demo for you. So, first question I have for you is, are homes and buildings wired in series or in parallel? Why don't you think about that for a second? Here's something to consider. If a light bulb burns out, it breaks a circuit. But if a light bulb burns out in, say, the building or in your home, does that make the entire home's lighting go dark? Does that make the entire room go dark? Okay. So if you're thinking to yourself that series, if you removed or broke the circuit on one of the light bulbs, that the rest of it would go dark, you are thinking correctly, which would make our homes and buildings like the school set up in parallel. So that way, if one light bulb goes dark, the rest of the room can still illuminate just fine, and all of the outlets work just fine. So, if we were to model a room like a kitchen here, okay? This room like a kitchen is set up with a toaster and a fan, and there's a blow dryer in there. We'll kind of ignore that. Most people don't blow dry their hair in the kitchen, but work with me here. We've got a couple of hot plates here, which kind of represent electric burners. A light bulb, I need a light bulb in the kitchen. Now, what we've got going on here is a circuit. This is set up as a parallel circuit with our light bulb, our hot plate, another hot plate, a toaster, a fan, and a blow dryer. Now we know that when you set up a circuit like this, you've got to draw your resistors like little squiggly lines here, right? So the resistors are set up in parallel to each other. We also have a power source here. Now that power source is showing, this symbol right here represents DC power. That's a battery for us, okay? So what I'm going to do is just swap this out. And that is going to be our AC power. So that's what's coming through our wires in our home, okay? So let's just say, a typical outlet has around 100, 120 volts of electricity. Let's just make math easy and say that this is 100 volts, okay? 100 volts. Now, if we wanted to identify how much current we're using, we could certainly do that if we knew the power in watts that each one of these devices is using. Now, as we start to get through here, okay, we're going to notice that current is certainly a limiting factor for us whenever we are designing an electrical system, okay? Just like in a river, if you put too much water down the river, it's going to overflow the banks, and it's going to ruin the banks of the river. Around corners, it's going to carve out all the dirt and rock and all that stuff, and really wash all that stuff downstream. So, back in the day, we used to use these pretty often. They're little fuses, right? So on this fuse, you've got a little tiny wire that's inside of here, okay? And there's glass, so you can see the wire, because you have to know if it's broken or not. Because if the wire is broken, then it's not any good. It's not going to complete the circuit. But it wouldn't light up like a light bulb, okay? It's just going to conduct the electricity from one side to the other. Okay, so these little barrel fuses are really handy. You might notice that there are some of these perhaps in your car or in some of your cords and things like that. Like this is a cord from a holiday string of lights. You'll notice that as I push this right here, that little tab right there is going to allow me to get access in here to the fuse, right? So if the little holiday lights go out, then there's a little fuse right on there on that. Now, I'm going to go ahead and get things going here. I'm going to plug in our system. Go. There we go. We got this hot plate going. I'll explain that in a moment. Now, back in the day, not only did we use fuses in homes, but the fuses sometimes looked like this. It was kind of a threaded fuse, almost like a light bulb, and you would just screw that into there. Now, you could look on the inside, right? So it had a little clear window, so you can see if the wire is broken or not. Because if the wire is broken, then the circuit is no longer complete, which means electricity is not going to flow. Now, what the design of these was for is that if you ran too much current through your home and wires were going to start heating up too much and perhaps melt and create a house fire, these guys, the little wire in there would break first before the wires in your circuit would break. Okay? So these are a stronger, tougher wire, can hold more current than this one. And this one is rated at 30 amps. Okay? Now, it didn't take people very long to figure out, hey, you know what, when one of these goes out in the middle of the night, I need to replace it, otherwise I have no lighting, and it could be 8 o'clock at night, 7 o'clock at night, right? You're not going to have lights the entire night. You're not going to have a circuit, because if you don't have an extra one of these sitting in a box somewhere, and you're at home, you got a real problem, right? You're not going to have, and if it's the weekend and the hardware store is closed, now you got a real problem. So what people started to realize is, you know what? Metals conduct electricity, right? They're conductors. And something that's metal that conducts electricity really well is a penny, right? So this penny right here, what they would do is take that little penny and throw it right in the spot where this one should go, and just unscrew this, drop that penny in there, and voila, they completed the circuit. Wow, my lights are back on again. But here's the issue. It didn't fix the problem. The problem was you were bringing too much current through your wires that was going to cause them to overheat and damage the wires, perhaps even causing a house fire. So people would remove this, and a temporary fix, throw the penny in there until I can get to the hardware store. Days, weeks, months perhaps would pass, and you're heating up the wires in your house over and over and over again, and perhaps to the result of a fire in your house. Okay? So obviously, really, really bad. So they said, all right, people are finding a way around our little fuses, right? They're putting pennies and things in there to conduct the electricity. What if instead we use and create a circuit breaker, right? So the circuit breakers, you can switch on and off, and if it trips, you just go out to your circuit breaker, click that back on again, and voila, your lights come back. Amazing, right? So now you don't have to replace anything. Well, what's in a circuit breaker? Well, a circuit breaker is just a switch like this, right? And this circuit breaker that's on here just happens to be a 15 amp circuit breaker. Okay? It's like a switch. It can hold 15 amps. It's got a little wire in here, a little piece of metal that is going to allow it to maintain that circuit, right? So when you trip this on, now the wire has just engaged with the other side. So when this is properly put into place, the wire connects. The wire, or the metal that's in there, is a thin little strip, just like this one. On one side of the little strip of metal is one particular type of metal, right? So a particular element, right? So, I don't know, it might be, say, copper on one side, and you might have iron on the other side, right? But they're fused together. They're kind of melted together, right? The two pieces of metal, they're different types of metal. And one thing that we do know, when stuff heats up, they expand. Well, different things, different metals expand at different rates, right? It just depends on the properties of the metal. And so with this little thing, this is straight. Imagine this being the wire, right? Or the little piece of metal that would be closing the circuit. If I put this on the hot pad and I heated it up, or hot plate, I'm not pressing down, but you can see that very, very quickly it bent. So what is the usefulness of this? Well, with this little bimetallic strip, it will break the circuit. Okay, it will break the circuit. Once it cools down, then it can come back in contact again, but as it breaks the circuit breaker trips. As that circuit breaker trips, and this little piece of metal cools down, eventually it's going to come in contact with that again, and then you will have to reset your circuit breaker. Okay? The whole reason this is happening is because this little piece of metal is heating up, but so are the little pieces of metal that are in the wires. And so this is a preventative method to try to prevent house fires, right? So what's going to happen is this little guy right here is going to trip, and not your wires melting and then perhaps contacting each other and creating sparks inside of your walls. So now you can see this little piece of metal that's cooled down sufficiently, so now it can make contact again. Okay? Now that it can make contact, you can turn that back on again, and everything should be good. Okay? So, let's take a look at what we've got here. We've got a circuit set up, right? This is not unlike what you would see in a room, right? 1, 2, 3, 4, 5 outlets, let's just say. This could be our stove, so you might not have an outlet there, but there's 2 burners on our stove here. You've got a light bulb. So, here's how it works, right? We're here, wake up in the morning, all right, man, I'm hungry. Go down to the kitchen, you turn on the light, right? Turn on the light bulb. This is a 150 watt light bulb. Okay, that 150 watt light bulb. 150 watts. If we do the math there, if we choose 100 here, and say we've got, we don't know the current, so we've got 100 on the bottom, and 150 on top for the power, because that is the power of the light bulb. Now suddenly we've got 1.5 amps. .5 amps. We can go up to 15 amps before the circuit breaker trips. So we're good. We got lots more to go. Now we're going to go ahead, light bulbs on. We're going to turn on 2 burners on the stove, electric burners. One of those is going to be, cooking up our eggs, and the other one maybe your bacon, right, or something like that. All right, so we've got eggs and bacon going. We've got 2 1,000 watt burners, hot plates. Those 1,000 watts, if we put 1,000 watts over here, divide that by 100, we get current of 10 amps each. So far we're at 10, 20, 21.5. We're already over what this can take. But we're going to keep going because, we're slow learners. All right, so now we've got our eggs, we've got our bacon, our lights on. We're going to go ahead and get our toast going, okay? Ooh, look, bacon is starting to burn. I'm going to turn the fan on because the fan is going to help, exhaust all the smoke and the fumes and all that stuff. So now I've got the toaster, and our toaster is going to be 500 watts, which is going to be 5 amps. Then we've got our fan, which we're going to say is going to be another 150 watts, which is another 1.5. So now, all told, we've got 10, 20, 25, 25, 26, 27, 28 amps going through our circuit breaker. And notice everything just turned off. Why did it do that? Well, remember our little strip of metal that's inside of the circuit breaker. These are still hot here, so it should work. Our little strip of metal curled up like this, and it broke the circuit. And when it broke the circuit, everything went off because our little circuit breaker here is kind of set up in series, right? It's a parallel circuit, but when this goes, you don't get power back returning in its full cycle. Okay, that's the problem. So, what we had here is a circuit with a light bulb, a hot plate, a toaster, and a fan, all in one circuit with only one 15 amp fuse, which is pretty common in a house. And we were able to blow that fuse. Now, what happens if I reset it? Everything comes back, check it out. But did I fix the problem? We still have our 2 hot plates. We still have our light bulb right here. We still have our toaster oven going. We still have our fan trying to exhaust the fumes from the bacon, right? What's going to happen? If you're thinking nothing, you're not right. If you're thinking something, yeah, you might be right there. What's specifically going to happen is our little circuit breaker right here is going to heat up again. Right? Just like this little piece of metal here. Our little circuit breaker is going to heat up, and it's going to bend that piece of metal. And when it bends that piece of metal, again, it broke our circuit. That is science in action right there. That is physics for you. All right? Physics, electricity, circuits, fuses versus circuit breakers Circuit breakers are a modern invention that are designed to help keep your family and your home and your buildings safe so that they don't burn down. Okay? I hope you learned an awful lot from today's lesson. Now you're going to have a document that you are going to be filling out, right, and answering some questions for us, and do the best that you can. You're going to be building a schematic just like this for us, and then explaining what's happening with a circuit breaker and exactly how they work. All right, Stanley Lake Physics, good talking to you. We'll check you out next time.